from the last time we discussed the phasors, okay, and how the phasors were used when we analyze the Maxwell's equations. And so we had Maxwell equations, and Maxwell equations, we had more or less at least 2 or 3 different representations. The first representation, it was when we write them in the differential form, okay? And the differential form, it involved 2 curls, sorry, 2 divergences, where we do the divergence of E, divergence of H, curl of E, and curl of H, right? So these are the Maxwell's equations. So in the differential form, then we have them, and this is equal to something for sure. Okay. Then we have the same set of equations in the integral form. The integral form, you know how we obtain them. We just apply the Stokes theorem and the divergence theorem to get what we are expected. And we strongly stress in this class that we care a lot about using more intuition than memorization. And with this, I mean the following. So from here, we know that if we are going to apply to convert this one in the integral form, since this is a divergence, we have to integrate the first. So this is equal to something. Okay, this is equal to something. This is equal to something else, and so on. Now we apply the divergence theorem to this one, to the first expression. And the divergence theorem, it is integrating over volume, integrating dV. Okay? So here we have the divergence of E over a certain volume. This is the divergence of H over a certain volume. And here we come the curl of E integral surface volume. Okay, we do a surface volume. And then we have the curl of H. And here again, we have a surface integral. Sorry, I said surface volume before a while. So this was a surface integral. Okay? And then we know for sure that these are going to be equal to EDL. Okay? Because we know that the divergence theorem and the Stokes theorem, when we are integrating them, we can rewrite them as the integral over a volume, which is meter cubed. It's converted to a meter squared. Okay? So this is surface area. And this means it's a flux, then we get H ds, okay? Here, this surface area is meter squared, so then we have the integral of E times meter. So here we get E dl, okay? And similarly here, we get H dl. Okay, so this is how so this is the second form of the Maxwell's equations in the integral notation. Then we have also the third notation, which we know that when the electric field or the magnetic field are not in a static condition, which means that they are changing as a function of time, then we can use the phasors, and it just simplifies them, and it makes it much more easy when we operate with them. And the phasors, what they are, is that they remove the time dependency, okay? So we include the phase information into the phasor, and since all the time moves in the same way for the electric field and the magnetic field, and we are sure about that, okay? We are sure that time flows equivalently for these two fields, so we can cancel it out. We can solve the problem using only the magnitudes and the phase, okay? So we know that electric field and magnetic field, they are not in phase with each other, which means that they don't reach the maximum or the peak value at the same time. So what we do is that we write a vector. So we draw a vector. So for example, this can be the vector E, okay? And we write the magnitude of this vector. Then here, we can have the magnetic field B, which can be delayed with respect to the electric field by an angle of 90. So the phasors, that's all that they include. They have the magnitude and the phase with respect to the two. But the term omega t, we never see it, okay? And when we talk about the waves, Now, when we talk about quantities, we change as a function of time. Well, first of all, they change as a function of distance, okay? Because why do they change as a function of distance? Can you tell me where it's written in the board that the electric field and the magnetic field change as a function of distance? Do you see it in the board? We see it here, right? So the curl of E, it's a space derivative, is d over dx. We know that, right? That's the unit. And the divergence of E or H is also a space derivative. So the moment that we see it, this operator, this is the then operator, this is the unit of this term is 1 over meter. So we are taking the derivative. So this is equivalent to delta operator over delta x, okay, where this is E. So, so the change on E, or we can write this one as EI plus 1 minus EI over XI plus 1 minus XI. You know numerical analysis, and this is the discrete form of expressing the analytical expression of the derivative. So we have a change. As a function of x, which means that we have d over dx. Okay? Then we started this course with deriving all the laws from electrostatic condition. Then we had the magnetostatic condition, and then we moved to the time where the electric field and the magnetic field vary as a function of time. And at that moment, we have now this, so this is different from 0. When we are in when time is a factor, we have also different from 0. Okay, so we have d over dx is different from 0, and d over dt is different from 0. The moment that we have these, then we are going to assume the conditions where the time dependency is time harmonic. Okay, with what we mean with this one is that we expect the behavior of the electric field and the magnetic field to have solutions that look like sines or cosines. Okay, of course they are much more complex than this, but for the sake of the second year bachelor studies, this is reasonable. We cover this one. In a more advanced courses using numerical analysis, you can deal with much more complex solutions. So we are dealing with time harmonic solutions. So given this, we mean the following. So electric field, we can represent it as E0 times e to the power I. So we have the exponential term, but these electric fields, they're not going to exponentially increase or exponentially decrease. They can actually, for sure, they should not exponentially increase. Okay, that's something which does not obey the conservation laws, and we don't have infinitely large sources of electric field. But the moment we have here a complex term, we see that this is not going to exponentially increase or decrease, but it's going to oscillate. So we have here e to the power omega t minus kx. Okay. So here we have these terms, and as engineers that you are, the first thing that you should do is that once you are given an expression, we try to carefully analyze it and to figure out what we are given. So here, there's an amplitude, and this is the way that it is going to oscillate, and it looks like the unit of omega, which is the angular frequency, which is measured as radian per second, is the inverse of the unit of time. Okay, so this means that the unit of omega times the unit of time is equal to what? Is 1. So the units cancel out. At the same time, the unit of k vector, which is called the propagation vector, okay, in a couple of textbooks you might find different vector used for k. You might see beta. So we have the unit of k times the unit of x. This is also equal to 1. So they cancel out each other, right? Because in the exponential term, we know that this should include no unit. Okay? So these concepts are also very important, and they are called reciprocal quantities or conjugate properties. So they are like inverses of each other. Inverse is not it is correct to some degree, but let's use the reciprocal term, okay? And you might see this relationship between omega and t and k and x also in the course of signal and systems. I'm sure you have taken the signal and systems, and you know that you can go from one representation, from the omega to the time using Fourier transform, and you can come from this back to the other one using the inverse Fourier transform. Okay? Normally, I said that the wrong way because we use Fourier transform to go from time to omega, okay? And we come backwards with inverse Fourier transform to time. Similarly, from x, we go with Fourier transform to k space, and from k, we come backwards with inverse Fourier transform to get the representation in terms of x. Now, these quantities, which are conjugate or reciprocal with respect to each other, we see those in this behavior of the electric field. Okay, so they are related to it with respect to each other. And now, since we started, so with this short review, I think it's good if we see a couple of examples. Okay, let me keep this one for a few more seconds, and let's see what we get for a second. So we said that the phasors, they don't have the time, right? This one, we might take it out for a second. So let's assume that we have this electric field, which is pointing. The electric field is pointing in the y direction. Okay, this is the direction of the electric field, and this is also a vector, and this is going to be equal cosine omega t minus kz, and the unit is volt per meter. Let me ask you one short question, and I want an answer from you. Let's say, what would you say if this expression was like this, cosine t minus kz? Would this be wrong? What can you conclude here? Huh? Oh, Kevin, thanks for your answer, but it could be that, not this wrong, but it could be that the omega, the frequency is 1, okay? So if the frequency is 1, then this could be right? But Kevin, thanks for your comment. Similarly, it could happen also that k can be 1, but the question is, does it really happen? The k and the omega, they are strongly linked with respect to each other, and the properties of space. Why do I say the properties of space? The properties of space, they are important because we know that the relationship between the omega and the k, they are linked with the speed of light, okay? And just for a moment, let's assume for a moment the following. So how is time and z related? We know that time and z is equal to the speed of light times time, right? Because we're talking about the waves. And similarly, the omega and k are also related like that. So, so the unit of k, actually, we don't know, you can do this as an exercise at home, check what is the unit of omega, and try to deduce a relationship between omega and k, okay? But now, let's move forward. This was just something that you should be really careful when we analyze this. So given this electric field, what is the phasor representation? So what is the phasor representation of this vector? So when we write the phasor representation, we have to write Z T. We should not have the T, okay? We should not have the time representation. And this is going to be equal to AY, okay? This stays the same. And we have to express this one in exponential terms. Okay, so this would be the respective representation. And then let's assume that we have another field which is magnetic field intensity as a function of x and time. And one other thing that is worth noticing is here that the electric field, it is pointing in the y direction, okay? But it depends on it does not depend on y at all. It depends on z. And the reason that it depends on z, and this would be a good question for you to ask, is that the E is changing as the wave is propagating along the z direction. Okay? So this is the direction of E, but the electric field does not depend on y. Now let's see another example. Okay, so let's assume that we have this other, let me say, this other vector field, and the phasor is going to be the h of x as a vector. This is equal to ay, so this is pointing along the ay, times the magnitude, which is 0.1 ampere per meter, because that's the unit of the magnetic field intensity. And then we multiply this one with the okay, so this would be the representation. Then so let's assume that we have an electric field now, which is as a function of y. So if this electric field is a function of y, this indicates that this is a phasor. Okay, so apparently it's not depending on the time, or the time dependence is not shown. So here we have 5 e to the power minus j 40 pi times y. Okay, so the electric field should depend on y. So this is the phasor notation, and given this phasor notation, we need to find what is the real-time dependency. So we are looking for this. What is E as a function of y and time, given the phasor notation? So if this is the phasor notation, we know that this is going to be equal to the real part, okay, of the phasor, which is Ey times e to the power j omega t. Okay, so this is going to be the time dependency, and then all we do is that we just follow carefully with this step. So here we have the Ey, the direction is the same. Here we get Az. Then we have the amplitude, which is 5. And then we have the e to the power j. Here we have omega t minus 40 pi 1. Okay? So this would be the real part, but then since here, sorry, we forgot to put here the real part. It's not done yet, right? We need to identify the real part here, because the real-time dependency, this should include no exponential term, okay? So it should be good looking, and this is going to be equal to, so what is the real part of this term? We get that this is AZ times 5, and the real part of an exponential term is equal to cosine, okay? So this is going to be equal to cosine omega t minus 40 pi y, okay? So this is the real-time dependency for the electric field. And for this, we try to remember that we have these relationships. So e to the power I theta, this is equal to cosine theta plus I sine theta. And the real part of the e to the power I theta, this is equal to cosine theta. And the imaginary part of e to the power I theta, this is equal to the sine theta. Okay? So this is how we can move around. And then let's see what we can, if we can see another example. So let's assume that we have an electric field which depends on Z and time, okay? So if this depends on Z and time, that means that the wave is propagating along the Z. This was wrong, sorry. This is a function of these, this is this, and this is equal to AY times the amplitude, it's 0.02 times cosine. So since we have here the time dependence, this cannot have phasor representations. This cannot have e to the power I something else. Okay? So here we have cosine times 7.5. Let me write it like this. 7.5 times 10 to the power 8 times time minus beta z, okay? And the unit of this one is volt per meter, okay? We know this part, this is volt per meter. The question is to find the HZT. So the question is, what is this? And the other question is, what is beta? Okay? So there is an importance, just for the moment, I think from a previous example we covered in the previous session, we saw that this beta, it is linked with this omega. And by the way, once we see this expression like this, we know two things, okay? Or actually we know a lot of things, but we know that this is omega. So right away, so this is the question. Given this, find this. So we are given this expression, and we need to find this part. Okay, then given the one on top, find the one on the bottom, the second line, and then let's list, just for our reference, let's list the given information, or the information that we already have, okay, by intuition. First of all, this omega, this is equal to 7.5, okay, times 10 to the power 8. And the unit of this one is radian per second. Radian is not a real unit, so it does not cancel with anything, but it's hertz, or it's 1/2. And this is also equal to 2 pi times frequency, okay? So this is 2 pi times frequency, and then and this has units, as we said, radians per second. And if this is radian per second, we can ask, yeah, I think we can, so we can find also what is the frequency here. And it looks like we know that 2 pi is equal to the around 6.28, right? If it is around 6.28, it looks like this is a time harmonic field. But what is the frequency of this time harmonic field? It looks like the frequency is something like 10 to the power. This is the frequency is around 100 megahertz, okay? Because the frequency is in the order of 10 to the power 8, and 10 to the power 8 it's approximately 10 squared times 10 to the power 6. 10 to the power 6 is a megahertz, so we are in the order of 100 to 200 megahertz. That's the frequency we are dealing with. Good, so this much information we are gathering, but we also know that the speed of light is something like 3 times 10 to the power 8 also. This is the speed of light, meter per second. And why is this? Because we know that the speed of light, c, is equal to 1/μ0 epsilon 0 square root. Okay. So when we say that because of the medium, whether it can be a vacuum, so these values are for vacuum, and this speed of light is also for vacuum. So if we are in some material media where the permittivity and permeability change slightly or a lot, then these values are going to be modified. Now, with this intuitive approach, we can start to find what is the H, okay? And now these harmonic dependencies, where we have the E and the H, they are linked with respect to each other because they are coupled in the Maxwell's equations. So in order to find those, we need to identify what is H. So first, well, and as a first step, let me see what part of the board you can see. So first step, we need to write EZ, okay? What this means is that EZ, we need to identify what is the phasor. And this phasor is going to be, this is equal to AY times the amplitude, which is 0.02, okay? This is the amplitude. And then we have e to the power minus I beta 7, okay? This is the phasor of the electric field. The second step, we need to find, we need to find H from E. And H, in the phasor notation, this can be written as, this is equal to -1/I omega μ0, the curl of E. Okay, the curl of E, and this is equal to, we need to identify this one, and let me think just for a moment, yes, the curl of E, yes. Now, the electric field here is 0. Here it is 0.02 e to the power minus I beta z. And the z component of the electric field is also 0. So then this is going to be equal to, so these constants, we know what they are more or less. And let's continue. So here we get that this is, let's keep this constant, -1/I omega μ0, and times, let's see what is the AX component. AX component, we have here that the derivative of 0 with respect to y minus the derivative of this term with respect to z. So here we get 0 minus, so here minus, the derivative is minus I beta times 0.02 e to the power minus I beta z. Okay? So this is how the derivative of this quantity is found. Then we have minus ay. So we do minus ay. And here we have the derivative of the 0 with respect to x and the derivative of 0 with respect to z. So this is 0 plus az. And plus az, let's see what we get. We have the derivative of this term with respect to x. And we see no explicit dependence on x here, so this is 0, minus the derivative of 0 with respect to y, so this is also 0. Okay? So then this whole expression, this is equal to minus 1 over I omega mu times, we get minus minus, we get plus, so here we get I beta 0.02. This is the amplitude of the electric field, e to the power minus I beta z. Okay, so we found the h. Now, if this is the h, we can cancel out the i's. So allow me to cancel them like this, or let's keep them for a moment and write that h is equal to 0.02 beta, 0.02 beta, divided by, we need the minus, omega times the permeability, mu 0, e to the power minus I beta z. Okay? So this is the h. Then the next step is we can identify what is E from H. Okay? So we wrote this, and so in fact this is almost enough. Okay, so in order to identify this first requirement, we are done. So we did this, but to get more detail on what B is, it is good to derive from this H to derive the E. Okay, so from here we can write what is E. Okay, we are going to see this just in a moment, why this is so useful. And for this, we write an expression which is similar to this one. So we get this expression, and here we can write that the electric field is this is equal to 1 over j omega times permittivity times the curl of H. Times the curve of H, and then we follow the same steps. Okay, so we write down this matrix looking like structure, and then since the H, it has, sorry, we have forgotten something very important, which is the direction of H. Okay, it's not clear, but it should be AX, because this was the only non-zero term. So let me put here AX. We should not have forgotten this one. So let this be AX, and this is equal to this. Okay. And then, and by the way, let's have a look actually what we have so far. If we construct, this is X, or let's do it like this. Let the X direction be here, let this be the Y direction, and let this be the Z direction. So what we have so far, we have an electric field which is pointing along the AY, like this. We have a magnetic field which is pointing upwards, like this, okay? And then we have, but we have, sorry, this is with a minus actually. Allow me to correct this one, because this is minus times AX. So minus AX, the magnetic field is pointing downwards. Okay, let's do it in red. And it looks like these two waves, the electric field and the magnetic field, they are propagating along the z direction, okay? And the z direction, the k, the propagation vector k, or actually here it is hidden as beta. And there is a reason why it's beta or k. You're going to see this one a little later. But for the sake of not being confused, or at this stage of our studies, let's assume that k, it is equivalent to beta. The reason is that for some, we are dealing in the cases with vacuum, okay? But there are some materials which are conductive, and if they are conductive, they are considered to be lossy. If they are lossy, the conductivity is a complex number. If it is a complex number, then one of these becomes a complex number, okay? And things behave slightly strangely. But just know this one for the moment. The kx or beta x is a term that you might see in the harmonic solution of the E and B. Good. So now, what we can say, I'm going to delete this very soon. So the direction of K is always going to be equal to the direction of the electric field cross product with the direction of the magnetic field. Okay? And let's check here. It looks like the E is pointing in this direction. If you use the right-hand rule, the Z is moving in this direction because this is AY, the H is minus AX. Okay? Probably I should write this a little better. This is minus AX. This is minus AX, and the H is equal to this expression. Okay. And then, yes, okay, that's good. So we take this out because this was just a small reminder of what K and B can be related. And if we substitute all the terms here, what we get the following. We get AY for the electric field times 0.02 beta squared over omega squared times the permeability times the permittivity times e to the power minus I beta z. Okay? So we found what is the electric field as a function of H. Now we get this, and then the next step, what we need to do is that at this stage we can answer this. What is the beta? Okay, and to answer what is the beta, all we need to do is that we need to equal this expression for E, because let's not forget, we started from an expression of E. We found H, and from H, we found E again. So, if we did no mistakes, these two terms should be equal to each other. So this and this, okay? So if those are equal to each other, let's have a look. We know omega, okay? This was clear from here. We wrote it right away. We know mu zero, we know this value. They are the values for the vacuum or for air. So the only thing that we don't know is the beta, okay, which was a question for us here. So with all of this, these two relationships, what we can do next is that we can equal this expression here on top, and we can say that 0.02, which is in the expression of E, this is equal to 0.02 times beta squared over omega squared mu 0 epsilon 0. Okay? So this is the relationship that we can construct. And then the thing is that these cancel out, and if you remember, we discussed before a while to notice what is the relationship between the omega and the beta. Somehow we are getting it from here. So the beta, it should be equal to the omega times square root of mu 0 epsilon 0. Okay? And because we can multiply both sides of the equation by this term, and we can take the square root, and then omega is 7.5 times 10 to the power 8. So 7.5 times 10 to the power 8. Times this mu 0 epsilon 0, this was the speed of light, right? So this whole term, we divide this one by the speed of light, which is 3 times 10 to the power 8. So these cancel each other, and beta, it looks like it's going to be something like 2.5. And the unit, so this is 2.5, and by the way, it looks like the beta is equal to omega over c. Okay, so this is how, apparently this is how these two quantities are related with respect to each other. And then, what is the unit here? This is 2.5. The unit of omega, it was radian per second. This was radian per second. And we divide it with the speed of light, which is a unit meter per second. So here we have meter per second, the unit of the speed of light. Seconds cancel out, and it looks like the beta, it has a unit which is radian per meter. Let's write this equivalent to radian per meter, 2.5. Okay. So we found the beta, we found the unit of beta, and everything that we cared so far. And then this part, let me see. So this part, it includes the calculation of E as of H as a function of E. I can erase this one because I think we did a good job there. And the conclusion of all of our steps, they're shown in what you see here on the board. And meanwhile, let's have one final look at this expression. This is omega t minus beta z. Okay? So let's have a look here. We notice that the z, so this is, what is z? Z, we mentioned before a while that the connection between z and time, they are through the speed of light, right? So this is equal to Ct, speed of light times time, right? So, and then here we notice that beta, it was equal to omega over c, or omega, it is equal to beta times c, beta times the speed of light. So here we can write the following. Instead of omega, we can write here beta times c, that's omega, times time, minus beta, what is z? Z, it was Ct. Okay, so apparently this is how these two quantities are related with respect to each other. And then if we check, we have beta Ct, beta Ct. Okay, so this is how these quantities are related, and it looks like you can have a look at it, and you can conclude. The only thing that is best to conclude for the moment is that they have the same unit, okay? Because now it became a little, so assume for a moment this is beta Ct minus beta Ct. So that's what we have in the exponential term, or that's what shows up in the cosine term. And by the way, mund të vendosja ato mungesat, nëse mund të vendosja ato nishat aty te tendence. Okay, so here we see this example, and I hope this is clear. Do we have any questions so far? Let's give him one second. Okay, so then let's see if we have any Any other example? Okay, well, let's see. So I think actually this one was clear. Any type of equation of problems that asks this type of questions, this would be the way to do it. Okay, so we just try to find the respective way how to find the magnetic field from the electric field and how to find the electric field from the magnetic field, and that's how we do it. Now, let's see another example, but the other example is going to deal with the relationship between the EMF and the flux, the magnetic flux. Okay. Let's assume that we have a couple of wires, okay, and these two wires, they're connected with respect to each other through a resistance R, okay, and then we have a magnetic field B that is going into the board, okay, so there's a magnetic field B pointing downwards, and what we do is that we can give we can assume this like a rail, okay? You can assume that these are the rails of the train, and you connect them at one end with a very large resistance, and then you get one of the, and this is conductive, and you get the wheels of the train. They are like similar to these push-up weights, which are used to test yourself how strong you are. Imagine that you just push it, okay? You give an initial velocity, you kick it with an initial velocity v0. Okay? But there is a magnetic field of Earth, and let's see what goes on with this case. So what happens here is that this is the rails of the train. This is a piece of metal which is conductive, and it's going to slide because you just kick it. You just kick it like that, and let's see what's going to happen. First of all, what happens is that this area, what is the initial area here? Area is, let's say, how can we know this one? Let's assume that this is some length L. Let me see if I have any how can I know this one? So let's assume that this is just L, okay? And this is some distance, this is X. So this side is X, and the area is Ls, okay? And then, if this one is moving, the area is going to change, okay? And then, what is the rate of change of the area with respect to the time? How can we find this one? This is equal to the derivative of Lx with respect to time, and in this derivative, the L is a constant, so we can take it out, and this is equal to the L times dx over dt, and this is LV, okay? So whatever the velocity is, the rate of change of the area as a function of time is the following expression. So the first question that comes to our mind is this: what is the current? that is going to flow in the resistor. Okay. Now, to find the current in the resistor, we need to identify what is the EMF. Okay. And we know that the EMF, the electromotive force, this is equal to minus the rate of change of the flux with respect to time. Okay. And the rate of the flux itself, so the flux, it is equal to B times area. Okay. The magnetic field times the area. The rate of change of the flux with respect to time is d flux over d time. This is equal to let me do it like this. This is d over d time of b times area, and b is a constant, so we can take it out, and this is dA over dt, right? Because b is a constant value. And then what we're left with is dA over dt. We found it here that it was equal to LV. So this is equal to B L times velocity. Okay. So this is d flux over the dt. Then this EMF, apparently, let's forget the minus sign for a moment. Let's write here BLV. So what is the current? The current that is going to flow over this resistor is equal to the EMF, the electromotive force, over the resistor, which is BL times velocity over R. Okay. So we found what is the current. Okay. Okay, we get the current. Then the next question is, let's find what is the force that is applied on this bar, on the blue bar. Okay, so the next question is this: force is equal to what? Now, the force on the bar, we know that the force between the magnetic force on a piece of circuit is equal to the following. So force is equal to I L B. Okay, the current times the length times the magnetic field. Okay, it's just a simple expression. Or we can also denote it like this: the infinitesimally small force is equal to the current times dl cross b. Okay, so the correct expression is this, in fact. But since the L is this length, since this L is perpendicular to the magnetic field, we can write it like this: ILB. Okay? In this case, if they are perpendicular, this would be IBL times B. So the force is ILB, and we can substitute what was I, and I, it was equal to BL times velocity over R. So this was the current times BL again. So there are these two terms. So it looks like the force is equal to B squared L squared times V over R. Okay, so we found the force, and then the next question that we can ask here is, in fact, what is, and this force is going to point like this, okay? And the reason that it's going to point like this is the following. So actually, we need to first identify what is the direction of the current. The direction of the current, it should be equal to the direction of the current. It should be in the same direction with the direction of the force on the charges. So the force on the charges is equal to Q V cross B. Okay. So this is the force, magnetic force, which is applied on a single charge, on a proton here. Okay. So if the initial velocity was v, and let's denote here the direction. So this was the velocity, the b is into the board. So if you use the right-hand rule, the force is upwards, okay? So let's also draw a coordinate system. Let this be x, okay? Let this be y, and the z is pointing out of the board. And then here, we would have, I saw a couple of comments, okay. So then this would be equal to the q, velocity is ax, okay, let's just notice the direction, cross magnetic field is minus az, because if we denote x and y like this, the z is going to plus z is going to point out of the board. But the b itself, it will be minus az. So then here we have that ax cross az, this is going to be equal to, let's see what we get. This is ax, ay, az. If we move clockwise, we get plus each time, okay? If we move clockwise, we get plus. Here we get ax cross az, minus az. We go counterclockwise, but we have a minus sign here, so this is equal to ay. Okay, this is, from here we see that ax cross az, this is minus ay, okay? But since here we have a negative sign, with a negative sign here, this becomes a plus. So the force here, the magnetic force, is equal to Q VB, and the magnitude is AY. So it looks like the magnetic force on the charges is moving up, which means that the current is going to flow like this, okay? Maybe it's better if I draw this in blue. So the current in blue is flowing like this. So if the current is flowing like this, then at this point where the force, so the current is flowing also in this direction, then here the force would be equal to, this is equal to I, dl is AY, cross, what is the magnetic field? It's pointing into the board, is minus AZ, okay? And the force that we're trying to identify is, let's see, AY cross minus AZ. Now, AY, if we move cross AZ, we are moving clockwise. What is AY cross AZ? This should be AX, okay? Because two subsequent one, we take the cross product, we find the third one with a plus sign. But here we have minus AZ, and this means that AY cross minus AZ, this is equal to minus AX, okay? So this is equal to, now these are just the magnitudes, this is going to be I dl times b, this is the infinitesimally small length, times minus AX. So this was the direction of the force, okay? So this was the force on the charge, this is the force on the bar, okay? On this current carrying element. So, and by the way, let's do this one, minus AX. Okay, we found the force. Okay, that's good. Now that we found the force, the next question can be the following. What is the velocity of the bar as a function of time? To find the velocity of the bar as a function of time, we need to write, so this one, let's remove this one. We need to write the Newton's second law, and that one is this. The force is equal to mass times acceleration. Okay? So if this is the force is equal to mass times acceleration, then this is going to be equal to, this is equal to mass times the rate of change of the velocity with respect to time. Okay? This is equal to the force. The force is equal the force is equal to B squared L squared velocity is here over r. Okay? So this is the Newton's second law. Mass times acceleration is equal to this force. Okay? And we need to solve this differential equation. And for this differential equation, we can separate this one. Separating a differential equation means to take one variable on one side and the other variable on the other side. So here we get dv over v. This is going to be equal to b squared L squared over mr times dt. Okay? So it is separated. We have all the variables of the velocity on one side and the time on this other side. And these are all constants. Okay? And then all we need to do is that we integrate on both sides of the equation. Since these are all constants, I can put the integration sign either here or here. Since this is a constant, let me put it here. Because constants, they can easily get out of the integral sign. And the integral of dv over v, this is the natural logarithm of the velocity. This is equal to b squared L squared over mr times time, okay? Plus some constant. Then we take the exponential on both sides of the equation. And if we do that, let's take out this simple calculations of vector directions. Then from this expression, we just take the exponential of both sides. We get the following. We get that the velocity is equal to v0 e to the power b squared L squared over mr. So here mr times. Actually, here we always had a negative sign. Negative sign, because this was minus ax times time, okay? So it looks like if we give an initial kick of velocity in this direction, since the force is in the opposite direction, this velocity will exponentially decrease from the initial v0, okay? And it's going to be exponentially decrease. And how fast the exponential decrease will happen, it will be determined by the relative magnitude of b squared L squared over the mass of the bar over the resistance. So let's not forget that R, it was the resistance. Okay, so this is just an application of these relationships. Now, do you have any question? Okay, if you have, wait a second. So I can just remind you to go over our textbook and to check, to go over the chapter, I think, let me check for a moment, to go over time harmonic electromagnetics in chapter 6 of the textbook, okay? Go over the examples, and I'm going to assign a homework from chapter 6 as the next homework. Okay, if there are no more questions,